Hi, my name is Giles Jacobs and I will present you the work Professor Hoster and I have done on extracting fine-grained economic events from business news. To drive data-driven financial NLP, we need more annotated data. I will present you the SENTIVENT dataset of annotated economic events and a pilot study applying a state-of-the-art model on our dataset. First, I will introduce event extraction, the task and what fine-grained events are in the economic domain. And then I will talk about the properties of our dataset. And finally, I will discuss the experiments and the results we have done. Event processing is the field of information extraction that tries to obtain structured information on changes in the real world. Historically, the main focus was on geopolitical events such as military attacks, judicial verdicts, elections, and so on. The ACE research program is one of the largest efforts in event processing. ACE organized shared tasks around extracting fine-grained events of general geopolitical nature. ACE was later followed by the Entities, Relations and Events program, ERE, which aimed to create more resources, improve annotation quality and push the state-of-the-art further. The ACE 2005 and to a lesser extent the ERE event datasets are dominant benchmarks for event extraction, and we made sure our annotation guidelines were compatible with them and based them largely on the rich ERE guidelines. Compatibility with ACE and ERE of our dataset means that we can more easily apply state-of-the-art architectures. So why spend the effort of creating an annotated dataset? Event resources are lacking in the economic text domain, and the current methods of event extraction reflect that. They are mostly all pattern or knowledge based, using handmade rules or ontologies alongside machine learning techniques. So to enable purely data-driven economic event extraction, an annotated dataset is needed. Now, what are these fine-grained economic events? Conceptually, we define an economic event as textually reported real-world occurrences, actions, and situations involving companies. Basically, this means that there are events, changes, happenings in a world or market on which financial news reports. The event annotations themselves consist of three main parts. First, the trigger, which are the words that express an event of a certain type. Secondly, the arguments, which express prototypical roles of the people, companies, things, and entities that participate in the event. These event types and argument roles are determined beforehand in a typology. And third, several event attributes are annotated. These are event main type, subtype, modality, negation, and event coreference. We will not experiment with event attributes today, but they are in the dataset. Today we will focus on event extraction as classifying both the triggers and the participant arguments. So in the first example sentence, Mueller was a CFO in January 2009. The token named triggers or expresses an employment event. In the second sentence, which is a headline, American Airlines reports load factor increase in May, shares gain. There are two events. One trigger is the load factor increase of a revenue event, and share gains triggers a security value event. The participant arguments express a prototypical semantic role in the event. In the first sentence, Mueller is the employee argument, which is being named CEO, which is the title of the job role, and in January 2009 is a time argument. Our SENTIVENT dataset contains 288 annotated articles on 30 different companies. These 30 companies were selected for sector diversification so that text is not specialized on one industry. And they come from the S&P 500 because spot prices, key financial data and market data is readily available for almost all companies in the S&P 500. So that would enable market research alongside this dataset. Supervised event extraction always starts from an event typology, which specifies the event types and their participant arguments. We created a typology using iterative refinement, and this yielded 18 main event types and 48 unique argument types. As you can see in the event type frequency overview, the class imbalance is fairly large, but that's a trade-off we took for representativeness. The smallest classes are dividend, expense, financing, investment, and merger acquisitions, and legal. The types profit, loss, revenue, expense, and sale volume represent the major metrics of financial reporting on the income statement. Other key metrics that fall outside these types are more industry-specific, specialized metrics are collected in the financial report type. Discussions of asset performance are captured by rating and security value. While we aimed for compatibility with ERE and ACE, there are several main differences with the benchmark ACE 2005 dataset. In size, our dataset has more annotated events than ACE 2005, but less documents, so we have a higher event density. This is because we have an event typology that is tailored to the domain, unlike ACE 2005, which has general geopolitical events in general news text. ACE also annotates entity types and restricts argument to these types. We did not include a preceding entity annotation phase. We also did not restrict event trigger annotation by morphosyntactic rules like ACE does. This has two advantages. Events are less constrained in the definition, so we get more coverage, and annotation cost goes down. Another significant difference is in trigger token span annotations. For ACE, triggers are all single token. We allow multi-token and discontinuous token spans. As a matter of fact, 42% of our triggers are multi-word triggers. The goal of the pilot experiments is to apply the current state-of-the-art in event extraction on our new dataset to establish a baseline. So the task is twofold. First, it consists of identifying event trigger tokens and classifying their event types. And secondly, the model needs to identify token spans of arguments and classify their argument role type. In our pilot study, we apply an existing state-of-the-art model for event extraction on our dataset. The framework we chose is called Dynamic Graph Information Extraction++ by David Wadden and co-authors. The model also beat the state-of-the-art in performance on relation and entity extraction in other datasets, so it seems like a robust starting point. The disadvantage is that we have to perform some data pre-processing to make the model assumptions fit our data. The DYGIE++ model assumes single token triggers because that's what the ACE dataset has. So we have to transform our multi-token triggers into single tokens. We did this by using dependency parsing on the sentence and selecting a verbal and nominal root or child token within the trigger span. The model relies on enumeration of candidate text spans as contextualized embeddings and incorporates local and global context to jointly model event triggers and arguments. The model enumerates candidates of spans and encodes them using a pre-trained language model such as BERT. With event propagation enabled, a graph is generated based on the model's best guess at the relations between spans in the document. The event graph has two types of nodes, trigger nodes and argument nodes. Trigger nodes pass messages to the argument candidates, updating those argument embedded representations, and argument pass update messages to their probable triggers. Without this graph propagation mechanism, the embeddings are recontextualized by bidirectional LSTM. The contextualized representations are input into a final two-layer feed-forward neural net for each classification subtask. We experiment with several variations in the model architecture. BERT plus LSTM uses the aforementioned frozen BERT embeddings with an LSTM as contextualization layer. There is no event graph propagation here. In the BERT fine-tune variation, we use supervised fine-tuning of the BERT transformer model on the end task. We also examine the impact of disabling the named entity recognition subtask in the pipeline. This removes predicted entity labels from being used as features in trigger and argument classification. Our SENTIVENT dataset does not contain manually annotated ground truth entity labels, so we used silver standard ones that are inferred from a pre-trained ACE 2005 model. We also replaced BERT with an in-domain fine-tuned BERT model called FinBERT by Arachi. FinBERT further pre-trains BERT on our financial news corpus and is thus a good fit for use in our experiments. Going on to the results. The best model variation is the BERT large model with LSTM, with the named entity labels as features enabled. This is also the best architecture for the ACE dataset. Fine-tuning decreases performance for both BERT and FinBERT, likely because of hyperparameterization and the trigger detector beginning to overfit before the argument detector is finished training. Event graph propagation also does not improve scores. When disabling the named entity subtask, we see that they do positively, the inferred labels do positively contribute to the score. Rather surprisingly, FinBERT did not improve scores in any architecture and BERT large was superior. Recently, other financial domain pre-trained transformer models have been released, which show better performance on several classification classes than this FinBERT model, so maybe this model isn't as qualitative as it could be. Comparing the best architecture with ACE, we see a large drop in performance. One of the reasons for the drop is due to the multi-token to single token pre-processing step, which introduces ambiguity into our dataset. Event type classes in our dataset often share lexical items and are differentiated by their full multi-token phrase. For example, the multi-token trigger conquer consumer spending is a sales volume type, but is reduced to just spending, which is also common in the expense type. ACE 2005 does not have the same problem as their single token triggers delineate general domain event types better. The local and global context modeling of the architecture did not work good enough to disambiguate the lexical ambiguity of triggers. And the higher event density of our data, in which multiple events often coincide in the same sentence, means there is less context to learn from, as well as a higher likelihood of overlap in lexical context of triggers and arguments. The multi-token triggers, the lexico-semantic overlap between classes, and context overlap make this a more challenging task. We performed error analysis on the event predictions and found that the largest error class were missed events and arguments. Spurious predictions are predictions made when none are present in the ground truth, which is the second largest error type, and misclassifications of types are a smaller problem. This error type distribution is fairly typical for event extraction. We also did manual analysis of some error types, and we found that the largest problem was indeed a single token transform. So in conclusion, we present the first annotated gold standard dataset on economic events. The pilot study shows that the current state-of-the-art models for ACE 2005 are not readily applicable with good performance to our dataset, which presents a more challenging task. We require the handling of multi-token spans when modeling our economic triggers. And in future work, that's what we'll do. So we'll incorporate handling of multi-token spans. We will improve the local context modeling for disambiguation of the triggers. And in ongoing work, we have also annotated investor sentiment on top of events, so we can process the common sense sentiment of events automatically. The source code and replication data for these experiments are available at the link shown. The fully annotated dataset is available on request for academic research, and it will be released later at the link after the project ends. Thank you for your time, and I am happy to answer any of your questions if you have them.